So these are the terms we're going to define. Remember, it's not just getting these terms down in the definition, it's also some concepts. I want you, when you're done today, to know how a transformer works. To know that, to understand that, you have to be able to answer this second question. What is magnetism? And the third question, how are they related? You need to understand that magnetism can create electricity, and electricity can create magnetism. And I love this whole business of how a transformer works because it's really a brilliant design. Whoever came up with the design for a transformer, because it takes advantage of everything that we've learned. First question I have for you, I want you to look at some common household appliances here and tell me which of these do you think run off of AC and which do you think run off of DC? Nathan?
The lamp and the fridge run off of AC,
Okay. You say this is AC and this is AC. Everything else you say is DC?
No, I think the radio is AC too.
The radio's AC too? Okay. Anyone have a different opinion? Yes.
I think the radio is AC or DC.
Okay. AC or DC. Anything else DC?
The DVD player and computer.
Okay. And the DVD player and the computer. All right. First of all, go ahead, Sedona.
Aren't they all AC?
Well, that's a good question. Don't they all plug into an outlet, a wall outlet? And what kind of electricity comes out of the wall outlet? Alternating current. We describe that current in a number of ways. I said it's useful to know these numbers. Do you remember what the voltage was of that electricity out of the wall? 120. So we have 120 volts. Does anyone remember how often it does this every second? 60. We call that 60 what? No? Hertz. Abbreviated HZ. That means it does 60 positive and 60 negative flows. Does that business 60 times a second. Okay? So we know something in our mind about that electricity. We know why it goes positive and negative. We know it has to do with the direction we're going through those lines of force. Back to this design with our generator spinning around. And we know that at some point it's going down through the lines of force, another point it's going up. That was the main idea about yesterday. All right, well, you're right if you said that all of those plug into an outlet. Some of them can run off of batteries, and you know that a battery is DC. But they all plug into an outlet. But the question is, what exactly do the electronic parts, the devices within all of those things, what kind of electricity do they really use? And the answer is, the refrigerator does use AC. And the lamp, a plain simple lamp with a light bulb, does use the AC. But your stereo boombox, even though it plugs into an outlet, it requires direct current, DC. Remember that the direct current, unlike the alternating current, goes up, stays positive. Okay? Actually, I did that wrong there. It's never down here below negative. It's always positive. And the computer also needs direct current. The DVD player also needs direct current. Okay? And you might find it interesting to note that all of these things are more what we think of as electronics. You know, they got some sort of little display here, you know, and they require a lot more circuitry, a lot more parts inside. These tend to be more simple. They have a motor, an element that heats up or cools, or they just make light. They don't have the same kind of electronics. What you'll see is the most common device around the house, on your body, electronic device, period, uses direct current. And the only way we've known so far to make direct current is with a battery. Well, thank goodness we don't have to power all this stuff off of batteries. Okay? What we do is we make a couple of changes. Not only can we change from AC to DC, so that we can plug these things into an outlet, but we also have to change the voltage. Remember, going into all of these, they plug into an outlet, is 120 volts. Okay? Some of them can use that 120 volts just fine, and some can't. The refrigerator, 120 volts AC is just fine. The lamp, 120 volts, AC, VAC is just fine. But when we start talking about this stereo, this boom box, even though it plugs into an outlet, eventually it needs to have, would you please stop that? I don't know what you've been doing all period long, tearing off the edge of your paper. Eventually this needs usually about 12 volts DC. 12 volts. So it's lower than what we're getting out of the wall outlet, and it's gone from AC to DC. The DVD player, well, that needs somewhere between 12 and 24. It's pretty common, volts DC. The computer, well, that's big, so you'd expect a lot of volts. Nope, 5 volts DC. Okay? So each one of those needs a different amount of voltage. All your devices in your house, even though they plug into an outlet, don't just run off of the 120. We need to change the voltage. And that leads us to a discussion of these guys, AC adapters. You get all that information down, you got a good definition for it. Okay? AC adapters are those black boxes. You see them all around the house. You know, you call it your cell phone charger. The thing you plug in the wall, you plug into the bottom of your cell phone. AC adapter. The thing you plug into a portable CD player or iPod. AC adapter. Those AC adapters are all over the place. All these things over here on this side, a little lightning plasma ball, this guy here, all run off of these AC adapters. Sometimes they have, you know, a box that sticks directly on the wall with a plug on that and then a cord on the other end, and sometimes it's got a cord that plugs in the wall and the box is somewhere along the line, and then the other end of the cord goes into your device. This black box is going to make two changes. It's going to adapt your device that's designed to run off of DC so it can run off of AC. The two changes it makes is it's going to change the voltage. 120 is far too much for most devices in your house. We need to lower it down. The computer needs 5, the stereo 12, okay? The transformer, transform means to change. The transformer is going to change that voltage. But the other problem we have is that the electronic devices, you know, all those things with the display and do all the beeps and all the fancy stuff, those things, they don't like it when the electricity goes past 0, when it changes directions, okay? It would be kind of like, you know, you drive your car over those little spikes they put in the road, you know, you can only go one way into the parking lot. If you go back out the wrong way, it tears up your tires. You guys know what I'm talking about? Okay? Well, that's kind of how the electronic devices would react if you gave it electricity going the wrong way. It might go pop. A little poof of smoke comes out and you've just destroyed it. Okay? It doesn't like that flow in the opposite direction. A light bulb doesn't care. A light bulb takes the positive and the negative flow. Doesn't matter, because all we have in a light bulb, you know, you just got that little filament wire, and the electrons are either going this way through the wire or that way. It doesn't matter. They're flowing. It's going to light it up. It's going to work just fine. However, for direct current devices like this computer, you run that electricity the wrong way, it's like, you know, driving that car back over those spikes in the road. We can't have this. So there's a device called a rectifier. To rectify means to fix or to change. And this rectifier is going to change this AC into kind of sort of like DC. We need to get rid of this part. And there's a simple way to just chop off anything that goes negative. We'll talk about that device later on when we get to this part down here. But it's called a diode. If we use 4 of those devices together, we make something called a rectifier. Now you don't need to know that part. I just want you to know what the rectifier does. It's pretty cool. It takes this part, instead of just chopping it off, it flips it over. Oops, my thing's out of alignment there. It flips it up like this. So now all the negative becomes a positive. Now you'll notice that it isn't the same as direct current. In direct current, our current goes up and it stays positive. Okay? This is going to have little peaks and valleys, but it never will go below negative. How many understand that? Raise your hand if you got that. So this is what a rectifier does. Inside this box then are two basic parts. A transformer. Transformers you might have seen before. They look something like this one here. Okay? Transformer. They're going to change the voltage. We're going to look at that in detail here in a second. And then some other little black parts that will change from AC to DC. On the outside of that AC adapter, you can read right off. It'll tell you 120 volts in, 12 volts out. It'll tell you whether or not it changes it from AC to DC. You can read right off of it. Now you're probably already thinking, well, you're not telling us the truth, Mr. Myers. You don't really know what you're talking about, because I know for a fact that my computer plugs directly into the wall. And there is no black box like this on my computer. Okay? Well, like your printer. How many of you have a printer that has a black box on a cord on the way to the printer, somewhere along the way? Some of you know you do, some of you may not. But you're right. Your computer does not have a black box like that on the way to the computer. Most of them, unless it's like a laptop like this one. Okay? I have a box right over here plugged into the wall. Well, where do you think that stuff is? It's in the computer itself. It's in the main CPU. In this big box down here is a big transformer. Pretty similar in size to this giant one. And that's why your computer is so heavy, your CPU is so heavy. There is a thing inside the box to change the voltage, to bring it down to the 5 volts the computer needs. There also, on the little circuit boards, are the little parts that do this, that turn AC to DC. So sometimes it is built inside the device and sometimes it's outside. Like your radio. You might just have a cord that goes from that radio to the outlet. Well, the AC adapter is built into that particular unit. Your clock radio, same thing. It's built into the unit. Does that make sense? Okay, let's look now at the transformers. Shake your head yes, if that makes sense. Okay, thank you. Let's look at the transformers and how they work. And this is getting into the theory. You got to be able to do a little math with this too. There's 3 different transformers we're going to talk about. All of them have something in common. They all include 2 what? Coils. We already talked about that as the symbol for a coil. A coil is an electromagnet. Okay? Let's look at this transformer first, because it's the most common kind. Okay, like I said, this is what a transformer would look like. And we'd have 2 wires going into it and 2 wires coming out. Sometimes there are transformers with more wires that's doing other stuff that I don't want to get into and confuse you. But this has 2 wires going in and 2 wires going out. And we have a name for the ins and the outs. The in side is called the primary. Primary. That's the input side. We call it the primary coil. The outside is called the, take a guess, secondary. It's like the first and the second. So the input is the primary, the output is the secondary. You might have noticed that the number of turns on these 2 coils are different. And they're different because our goal of this transformer is to change the voltage. Let me explain how that change happens. This particular transformer is called a, anyone want to take a guess at it? What kind of transformer? Zach?
It's a step-down transformer.
You got it. This is a step-down transformer. A step-down transformer will decrease the amount of voltage. It will decrease or reduce the amount of voltage. I would add to that definition, it always has fewer turns in which coil?
Secondary.
In the secondary. Always has fewer turns in the secondary coil. And I just think this is so cool the way this works. Let me explain. So we've got our step-down transformer with fewer turns in the secondary. The primary, this coil here, is the one that goes right to the wall outlet. Those 2 wires go right into the plug. Okay? So we might hook it up to 120 volts, let's say. And what's going to happen is the voltage that comes out of the wall, what kind of voltage is it? What kind of current is it? AC, alternating current. And when I say that, not only are you picturing this, but you're picturing that the current flows positive for a while and negative for a while. You're picturing that the little electrons, instead of running in one direction and continuing to go in one direction, you're picturing that they're going to go one way for a while, and then they're going to turn around and start going the other way. That's what happens in AC, alternating current. So when I hook up my current to this primary coil, it's going one way and then the other way. What is the smallest magnet? A moving electron, okay? If I have a bunch of electrons flowing one way and then the other way, not only do I have a magnet, but I have a the word I was looking for is a moving magnet. Moving? Moving? Okay. Do you see how this, having electricity flow through this wire and do this, which is exactly what AC does, is the same as having a moving magnet? If this little electron zipping through the wire is like a moving magnet, and I got a whole bunch of them, I've got a bunch of magnetism going back and forth. Now you're starting to get a clue. See any light bulbs come on as to how this thing works? I have a moving magnet. You already know that if I have a coil, like this coil here, and I have a moving magnet next to it, what do I get? I get current. I get electricity. Is it going to change it into DC over here? Well, let me ask you this. Does the meter still go back and forth in different directions? Yes. So is it going to change it to DC over here? No. It's only going to change the voltage. And the reason it changes the 120 down to a lower voltage is because I'm using fewer turns on this coil. There's more energy to be had here. If I had more turns on this side, I could pick up more energy. But I'm only picking up the little bit that I need. I'm bringing it down. I'm stepping down the voltage. Okay? Because I have fewer turns here, I'm not going to pick up as much magnetism. I've spread it out over this large area, and I'm only going to pick up a small amount of it. So the electricity flowing through the wire and changing directions is the same thing as a magnet moving back and forth. I just think that's so cool. Because otherwise, if I want to generate electricity, I've got to have, my magnet moving or my coil moving. There has to be physical movement. Here, I don't have to do that. I can pass the electricity over to this wire and the wire's standing still. Those two coils are sitting right next to each other and standing still. What's moving are the electrons back and forth, making moving magnetism. How many understand that? It's the main concept for today. I got about half of you that aren't raising your hand. Please be honest. Don't raise your hand if you don't get it. So it lets me know how I'm doing here, guys. Again, how many of you understand how I get the electricity from here to there? Okay, Matt, what don't you understand?
I get it somehow.
Do you understand that electrons are moving back and forth here?
Yeah.
That's what this is showing. This is going one direction, this is going the other direction. Do you understand that electrons are like little miniature magnets? Okay? Do you understand that when I move a magnet back and forth by a coil of wire, I get current that goes back and forth? That's all you need to get. Okay? That's the main idea here. I'm not trying to pick on you, but I just want to figure out where we're missing. Yes? Well, let me ask you this. If it's just a wire made out of copper, will the wire itself become magnetic? I mean, will things stick to the wire? No, any more than they would stick to your electromagnet to the wire part. They'd have to stick to the core part, okay? And if the core were made of iron, nickel, or cobalt, then yes, you could make magnetism, okay? All right, so now we know how we transfer the energy from here to here. Hopefully you can see that because this is a smaller coil, we're going to get less energy out here, less voltage. The question I have for you now is, what is that voltage going to be? And I'm going to show you a three-step process so you can figure out what the voltage is going to be. If we have an equal number of guys to girls in this class, what would you say is the ratio of guys to girls? 1 to 1. How many of you are comfortable with ratios? You've done that in math class. Yeah, I'm seeing most hands. We didn't do so hot with the math yesterday, so I'm not sure that I believe you. But if we want to figure out what the ratio is, the number of turns on the primary compared to the number of turns on the secondary, all you have to do is the following. Take the big number, divide it by the little number. What's the answer? 75 divided by 5.
13.
Try again.
15.
15. Okay? Take this number divided by this number. If we were doing it on this one over here, we take the big number divided by the little number. That's all you do. So I have a number, 15. Then you write that number next to the bigger number, 15, right there. I put the number I just found out when I divided this, the big number by the little number, I put it by the big number, and then I put a 1 on the other side. That is my ratio. Let's try it over here on this one. I had 10 turns here, 100 turns here. I take the big number, divide it by the little number, 10, and I write it over here by the big number. And I put a 1 on the other side. I have my ratio. Okay? Well, I don't have a big number or a little number, so I take 1 and I divide it by the other, and I get what? 1. Well, what is the ratio here? 1 to 1. We'll get to that in just a second. So now that I know the ratio, you can figure out what you're going to get. If you give it 120 volts here, are you going to get more or less here? What does this one do? Less. It's going to step it down. Now you got less turns, you're going to get less voltage here. So you either divide or multiply. So do you multiply this number by 15 or do you divide it by 15? Divide it by 15. Anyone know what that answer is? By the way, guys, I would hope that you would bring in a calculator. You're always welcome to use it in this class, and you will be using it on many occasions from here on out. Answer is 8. Melissa? Okay, so that was 120 divided by 15. Over here, if I were to give you 120 volts here, what am I going to get out on the other side? More or less? More. So do I divide or multiply by 10? Multiply. The answer is? Just add a 0. 1,200 in this case. And that kind of transformer is called a step-up transformer, as you might have expected. A step-up transformer, for your definition, has more turns in the secondary so that it can increase the voltage. Has more turns in the secondary coil so it can increase the voltage. Step-up transformer. And I'm going to give you examples for each of these in just a second, so you'll want to add that to your definition. But let's look at the last one here. If I put 120 volts in here, what am I going to get out there? 120. And you're probably thinking, well, what was the point? Well, what this does, what's kind of cool about transformers, is that the two coils don't actually have to be physically touching, nor do they have to be connected electrically. There isn't a wire going across here. So you can separate the two. You can isolate the two coils. And for that reason, this is called a isolation transformer. And I'll show you an example of where we use each of these. But at this point now, in addition to having those terms defined, all of the terms defined, you should also know how to come up with the ratio, like we did here. Big number divided by the little number, the answer goes below the big number. The other one's always going to be a 1. And then you should know how to use that to figure out what your voltage is going to be. If it's a step down, you're going to divide it by that number. If it's a step up, you're going to multiply it by that number. And if it's an isolation, well, you don't have to do anything. It's going to be the same answer. Here are some common examples of each of these transformers. The step down is the most common. That's the one you find in almost all of these AC adapters. because most devices around your house don't need 120. They need something less, 5, 9, 6, whatever. And so they're going to take that 120 and bring it down to something lower. Those green boxes that you see out in front of your house, some of you might have recognized these. Transformers, okay? They're going to take that high voltage that's on the power line and bring it down to a level that you need in your house. This guy here, and I'll get to you in just a sec. This guy here, Nikola Tesla, he's the one that came up with this whole idea of alternating current. He's the one that developed those early dynamos, generators. And it was Edison that wanted to do direct current and said that AC was dangerous and wouldn't work well. Well, AC works well for transmitting electricity over long distances. So we can have those power lines between cities and carry high voltage. So the green boxes are the things that you see as step-down transformers. In order to transmit that alternating current long distances, we need to have high voltage. We step it up at the electric company, and then we step it down at the houses so that you can get the 120, 220 that you need in your house for appliances. AC adapters, the little black boxes I showed you earlier, those are what you're going to find usually have step-down transformers. They don't need 120 volts, they need less, so you step it down. Step-up transformers are going to be found in a couple different things. Now you probably want to add these to your definitions, so you have some examples. A camera flash is one example of a step-up transformer. A camera flash needs a high burst of voltage, a lot of voltage. So we build up a charge and we store it. And it's really not that different from storing a charge when you scuff your feet across the carpet. Your body stores the extra electrons. In the flash, the step-up transformer provides a high voltage that's stored in another device called a capacitor. We'll talk about that later. And then it gives you a burst of energy for the flash to go off. Many of you may be familiar with cameras that have the little light that comes on and tells you when you can take a picture with the flash. Every time you take a picture, you got to wait a little while before that light comes on. That's the charging up part. That's like scuffing your feet on the carpet. Another example of a step-up transformer is a taser. So a taser takes a low voltage and makes it a high voltage. Most of those tasers run off of less than 24 volts. Like this 9-volt battery right here. The little tiny transformer you see here takes the small 9 volts and turns it into thousands of volts. Enough that you can feel an electric shock. You'd never feel that electric shock by touching the top of the 9-volt battery, but you will when you touch the tingler. It'll give you high voltage here. Now you're not getting something for nothing. You are increasing the voltage, but it requires current for that. So you actually use energy to do that. The transformer uses some energy to give you the higher voltage. This particular example is not going to provide enough current to cause any kind of serious damage. Just the voltage is what you feel as that pressure. You might have wondered why we have big and small transformers. A bigger transformer is not designed necessarily for higher voltage. It's designed for more current. Smaller transformers for smaller electronic devices that don't need that much current. The charger for your cell phone, for instance, has a very small transformer in it. The battery doesn't require much current. This transformer from a microwave oven has huge turns. If you look at the turns on the coil there, you'll notice that they're very thick wire. And that means it's designed to handle a lot more flow, a lot more current. Just like a thicker hose, a bigger hose like a fire hose will carry more water. So the bigger the transformer, the more current it can handle. You have to actually count the number of turns to know what it's doing, whether it's stepping it up or stepping it down. Our last type of transformer, the isolation transformer, the advantage again here is that we isolate. These two coils are not electrically connected. They are connected by magnetism. The moving magnetism here, the magnetic lines of force are going up and down, are being broken by the wire, and the wire picks up the electricity here. So now the two things don't have to be connected. You see this used in electric toothbrushes. Not all of them, but many of them will have a toothbrush that has a coil inside the handle. The case is sealed up so that no water can get inside. The base then is like a donut that surrounds that toothbrush, and that base has its own coil. So in essence, what you have is the base has a coil, the toothbrush has a coil inside it, you have one coil inside the other. So we're able to pass on the electricity that goes to the outlet to the batteries inside our toothbrush and charge it without ever actually being connected by wires. There's no wires to get wet or to be dangerous. They call this charging by induction. You don't need to know that, but it's a very useful thing that you can do with an isolation transformer, or with any transformer for that matter. In each of these cases then, you should be able to tell me, using math, what the voltage out would be. We did that with 120 volts. Let's try it again now with 150. The primary, the input, if it gets 150 volts AC, you should be able to tell me, if you know the ratio. Remember, this one was 15 to 1. I have 15 times as much here as I have here. I divide that by 15, I know I'm going to get 10 volts out. Over here, the ratio on this one was 10 times bigger on that side from this side. If I put 150 in here, I'm going to get 1500 out on this side. I stepped it up. And of course, on the isolation transformer, since the numbers are the same, the ratio is 1 to 1. 150 volts here will give me 150 volts here. That's transformers. That's how transformers work. You should have a definition for a step up, step down, and isolation transformer. Your step down definition should say something like the secondary coil has fewer turns, the voltage is decreased. Give an example like the green boxes or the AC adapter. For your step up transformer, you say the secondary has more turns. We can increase the voltage here. Example would be a flash in a camera or a taser. And the isolation transformer. The number of turns in the primary and secondary coils are the same. This allows us to separate the two electrically, and whatever we put in is what we get out. You should also know that an AC adapter includes both a transformer, usually this one, and a rectifier, something to change the voltage to the lower voltage we usually need, and something to change from AC to DC, current that stays positive. Remember that we do that by eliminating this bottom portion and flipping it over. We get what's called a pulsing DC. It stays positive, doesn't look exactly like a battery, but it works. Okay, next we're going to talk about motors. You're going to learn how this motor works. And every motor you will see has the following parts. Every motor must have a permanent magnet. It must have an electromagnet. You guys call it a coil. And the goal is it has to create continuous motion. In order for this to be accomplished, there has to be something in the design of the motor that does one of two things. The motor must switch on and off at the right time, or, in the case of this motor, we have to be able to switch poles. We're going to talk about both of these things so you can understand how a motor keeps going. To start that, let's look at the simplest design of a motor. This motor I have over here consists of a permanent magnet, one of our required parts, a coil of wire that's going to serve as an electromagnet, and a switch. The switch provides a very important function. Let's look at how this works. Right now, with the switch in the off position, I haven't pushed it down. I have no magnetism. I have no attraction between my electromagnet and my permanent magnet. When I activate the coil, I see an attraction. The north end of the coil is attracted to the south end of the magnet. Opposites attract. When I release the switch, it swings away. The force that makes this swing away from the magnet is not magnetism. Why? Because the switch is off. The coil is no longer an electromagnet. The force that makes it swing away is gravity. Gravity wants it to swing back to its original position. So if I time it right, I can keep the motion going. I can attract it and release it and keep the swinging motion going back and forth. While this does technically meet my definition of a motor, it's not very effective. It wouldn't do much work because the only real force of any consequence is the magnetism created when I press the button. The force that makes it go in the opposite direction is gravity. I could, however, improve on this design by putting another magnet on this side. Imagine this now. Instead of having a switch that turns on and off, imagine that I'm able to change the north and south poles on my electromagnet. If I could change them at will, I could make this coil decide which way it wants to go. I could have it be attracted to one magnet, and then if I switched the poles, if I made the poles the same, it would now be repelled. And I could have it attracted to a magnet over here, and then switch its poles again, and then be repelled. So I would have this shoving match going back and forth. Not only would the coil be pushed away from one magnet, but it would be pulled by the other one at the same time. And then the wires would switch, and once again it would be pushed away or repelled by one magnet and attracted by the other one. When you have two magnets working with a single coil at the same time, and you're able to switch the poles, then you have an effective motor that has power, can do some work for you. Okay? In order to accomplish this, in order to change the north and the south pole, I would have to physically change the wires that plug in to the battery. If I switch the wires, I switch the poles. That's not what I was doing with the switch. This switch was turning it on and off. Now the motor you're going to build is like this simple one I showed you just a second ago. It's going to switch on and off. You want to look for how that is accomplished. The motor that I want to show you now accomplishes its motion by switching its poles, changing its poles. In this real motor, this motor demonstrator, you can see now we've moved up to 2 permanent magnets. So now it's just not a matter of pushing and releasing, it's pushing and pulling. And not just from one side, this side can have the ability to push as well as pull, and so can this one. That's accomplished by changing the wiring. When this is hooked up to electricity, one wire will be positive and one wire will be negative. And one pole will be one polarity, north or south, and the other one will be the opposite. So when we hook up electricity to a coil, we get a north and a south pole. If we want to change the poles, one of the advantages of an electromagnet, all we have to do is change the wires. We can change the polarity, we say, of the poles. If you trace the path of this wire, you can see that it comes down and connects through this little metal flap called the brush, just like the brushes we had in our generator. I showed you previously that a generator has to have a way to keep the wires from getting tangled. Okay? Remember, we crank the handle, we get electricity, and there has to be a way to do that without these wires getting tangled up there. If this were permanently attached to our connections, the wires would get tangled. Instead, we use those little connections called brushes. You saw them on the green one I showed you. I also pointed out that when you take a generator and you hook it up to electricity, you get a motor, you get motion. They basically work the same way. One, you crank the handle and it generates electricity. The other one, you give it electricity and the handle cranks. So if you understand how a generator works, you have a good start in understanding how a motor works. Now let's break this down. Let's see how we're able to switch the wires on this particular coil. Remember, by switching the wires, we also switch the poles. And as you can tell right now, these two poles would repel and would attract, and these two would attract. If I switch the wires and the blue comes over here and the red comes over here, then they would be repelled and repelled. So I can change what's happening on any given end. In this picture, you can really get a view of how the switching is accomplished. Right now, if one wire comes down and connects to this flap, it's going to make a connection to this half of the ring. The ring has been split. It's like this. It's been split in half. One half of that ring comes down here and connects to this end of the coil. The other half of the ring, this part here, connects to this end of the coil. Notice that this flap here touches that half of the ring and goes off to a different wire. So as the coil rotates, every time it makes a 1/2 turn, we're going to switch. This will now connect to that side, and this will connect to that side. Simply by turning that coil just half a turn, just a little bit more this way, boom, this side is going to attach to the other side. In essence, by turning the coil, this wire then would be connected to this side. And this would become blue, and this would suddenly become red. And what would happen here would be different. Instead of being attracted, it would be repelled. Let me show you again step by step. In the first step here, I've attached my wires and I get a north and a south pole. If the poles are alike, likes repel, this is going to want to repel. Not just on this end, but also on this end. It's going to push away and that's going to push away. And our motion starts. And it continues to turn, trying to get away from the like poles. When it reaches the halfway point, the repulsion becomes less important as it starts to approach the opposite pole. Opposites attract. The blue is going to be attracted to the red, and the red is going to be attracted to the blue back here. And that will bring it all the way around. Now, if it wasn't for our special connections up here on this collar, our coil would only turn halfway around. It would start here and turn halfway around. Once we got to this point, the blue and the red would be attracted, and the red and the blue would be attracted, and the coil would stop moving. It would freeze up, which is exactly what you saw on the motor I made, the swing motor. When I held down the switch, the coil just sticks to it. It no longer swings back and forth. Fortunately, though, when the coil gets halfway around, that happens to be the exact same time that this wire going to this side now connects to the other side of the ring. And what that does, you'll notice that my pole that was blue becomes red. The poles have switched. It's just like taking the wires off and switching the connections. We make now this end red and this end blue, and once again, we're like we were at the beginning in step one. We're repelling, and the motor continues to spin. So once again, in order to keep that motion going in a real normal motor, we're going to want to switch the poles. We're going to want to change the connections to change whether we're being repelled or attracted. And we have to do it at the right point in time. And the motor you're going to build in a couple of days, it's going to keep going because gravity will make it go back, and your switch will allow it to be turned on at the right time. It's like pushing a child on a swing. And I'm going to ask you a question on that lab. How is it accomplished? How do we switch on and off the motor at the right time? Look for something similar to this. It's not going to switch the poles, but there is a way by the motion of the motor alone to change something.